All right, I heard 5. What else? Okay, somebody. All right, I'm starting with 5. Okay. You don't need your computers for the next maybe 10 minutes or so. So just halfway shut them so I know that you're not just doing whatever. Not that I don't trust you. It's just a thing. All right, so forgive me. I'm going to scroll past. No, it's still on. I'm going to scroll past some of this. I'm going to start with 5. Okay, can someone tell me the data? Because I don't have my phone. I don't have the problem set right here. What does it say for number 5? Never mind. Concentrated sulfuric acid, 18.4 molar, has a density of 1.84 grams per milliliters. After dilution with water to 5.20 molar, the solution has a density of 1.38 grams per mil. Blah, blah, blah. Calculate the volume of the concentrated acid required to prepare a 1 liter solution of the 5.12. So if you have molarity and volume, molarity, and it's kind of giving you some information to think about how to prep a solution. You're probably thinking about volume as well. So that's MV. Hence you have the dilution equation, again, because you are diluting the sample. It might be a little hard to see this because my projector is starting to die, but 18.4 molar times X, because that's your concentrated solution that you need, or a certain amount of it that you need, and then equals 5.20 times 1 liter. Divide, you get 282 milliliters of that concentrated solution to prepare the diluted solution. And it doesn't say, like, talk about how to prepare, but what would we do with this? What's the safest route? We have 18 molar acid. Go. Attain a 1 liter volumetric flask and how do you add? What's the little add acid to water, do what you oughter. Right. Add acid to water, do what you oughter. So what would you put in first then? Some DI water, I don't know, 200, 300, 500 mils, something like that. And then you'd add that mils of acid. And then add water to the etch line, Paragomenberg mix. Done. Okay. Part B, determine the mass percent of sulfuric acid in the original concentrated solution. So this is where you kind of have to pull apart the molarity because it's really given to you as 2 independent units if you think about it. Molarity is moles per liter. So I assumed a 1 liter sample because if you don't have a volume of the original, I will tell you always to assume 1 liter because that kind of gives you an easy number to work with. Thank you, Chase. And then assuming that 1 liter solution, that means you have 18.4 moles of the sulfuric acid. And so since that's pure sulfuric acid, you can convert that using its molar mass, 98 grams per mole, to 1804.3 grams of sulfuric acid pure. And since the whole solution was 1,000 milliliters, because that's what a liter is, given the molarity initially of 1.84 grams per mil, 1,000 times 1.84 grams per mil of solution, that's not pure sulfuric acid, that's like the dilute or somewhat dilute solution, you'll find 18.40 grams is our total solution, times about 100 to get mass percent, and so that's grams of part over grams of whole, and you get 98%, or 98.06. But that should make sense because this is super, super, super concentrated. It's going to be a very high percentage of the concentrated sulfuric acid. And then next, you have, okay, so a neutralization reaction. So essentially, if you have a neutralization process, you have to write the reaction out. So we have sulfuric acid and sodium bicarbonate, baking soda. And this was more like a titration review question, or an equivalence point review question. So if it says you're given this molarity, and it wants to know how much of this do I need to neutralize that, basically it's saying, like, if I were titrating this, how much volume would I need to fully react 100% all the base, because this sodium bicarbonate acts basically. So it's a 1-to-2 ratio. Starting off with your given of grams of sodium bicarbonate, go to moles, moles to moles, 1-to-2 ratio. Use your molarity in an inverted fashion to cancel out moles of sulfuric acid to get to liters, and then it makes more sense to write this number out in milliliters just because it's small. Thumbs up? Okay, and then molality, is that the last one? Molality, and what's the units for molality? moles of solute over kilograms solvent. So you have to segment this. This is why this is a little longer. This was the diluted sample, so assuming you have a 1 liter solution, again, is your best route, and you have 5.2 moles of sulfuric acid in that 1 liter solution. So your job is to figure out in that entire solution what part of that is actually solvent. It's not going to be very, or yeah, it's not, it shouldn't, well, no, this is more diluted. It's going to be a kind of a significant number here. So if your whole solution had a density of 1.38 grams per mil, take your 1 liter solution, convert to grams, you get 1,380 grams full solution. Given the moles of sulfuric acid, you can convert that to grams quite easily using the molar mass again, 509.9 grams of sulfuric acid. What's the difference? So this is sulfuric acid, this is solution. What's the component that's the difference in these mass? Water, right? Water is your aqueous solvent that you're utilizing. So mathematical difference would be the mass of that water. So the total mass minus the sulfuric acid mass will give you the solvent mass. That solvent mass is the piece you care about for the denominator of molality. And I cut it off here. So 870.1 grams of water. Back that thing up 3 times, you get kilograms. So that's 0.8701 kilograms of water as your solvent. And so the moles of solute over kilograms of solvent gives you molality of 5.98. Okay, so is this number close to the molarity? What was the molarity of the solution? 5.2, right? So it's relatively close. What you'll find is a lot of times our concentrations will be close when they're establishing molality, but they will usually never be the same because one's temperature dependent and one is not temperature dependent, and they deal with different units. Okay, so if you give that one, you're probably good. I will indicate some more help on some other pieces maybe shortly, but I know a couple of you guys need to kind of catch up on work too, so this will give you a chance to catch up on the factors of concentration. So what are all the units of concentration we could like give information about? Molarity, molality, mole fraction, mass fraction technically, right? What else? Mass percent. There's one in your printed notes we didn't talk about. It has like a whale next to it. Look in your printed notes. Parts per million, parts per billion. There are 2 others, and I did not talk about that Friday because we were running on fumes. I could tell you were done. But this is an image from your textbook that gives you a lot of good pieces on like just a comparison of the units that we would utilize. And down here, well, I will just tell you to compare and contrast. The fact that volume is utilized, it makes something temperature dependent because volume, it can be contracted or expanded by increasing or decreasing the temperature. Think about it, right? If you heat something up, it starts to spread out a little bit, so volume can change, therefore it's temperature dependent. And then that makes, why is molality not temperature dependent then? Okay, the solvent's not established in volume, it's established in kilograms. And then another one that we use that you guys can state is the parts, or the volume percent. So we can do mass percent, just mass of part over mass of whole. We can also do volume percent. Where have you guys seen that, like in everyday life? You've probably seen this. Yeah, like alcohols. If you've ever like gotten, or hydrogen peroxide, like you buy the 3% hydrogen peroxide off the shelf, that's percent by volume. Different alcohols, like rubbing alcohol, ethanol, anything like that. It's like 95% blah alcohol. Because they want you to know it's not pure, but they also need you to know 35%. And then for the sake of just noting that you know how to do parts per billion or parts per million, they'll establish a number. So like this example is 36 milliliters parts per million. So literally it's just that many milliliters over a million. So if it's 36 milliliters, it's over 1 million milliliters of that total solution. Okay, where is this utilized in everyday life? Okay, yeah, they talk about air particles. They talk about the purity of the air based on parts per million of such and such contaminant in the air. Drinking water, when they have different contaminants spilled into lakes and rivers, they test it to make sure that there's not over a certain parts per million, because it would be toxic to us, and then we have to shut down our water supply, find new ways to achieve water, or everybody buys bottled water. You remember that, like from West Virginia, they had the coal ash put into the water. That was probably a little like six or 8 years ago. More recently, they had sorry, what's your like that? 10? No. Yeah. All right. Well, anyway, so when my sister was in med school up in West Virginia, not a great place to be, just saying. It's an interesting place. They had like a coal ash village. She was like, I have to take showers in bottled water. I was like, I'm sorry, but that's the best thing they can do for you. And so she was upset, but they had to. And then also, if you ever think about mercury and seafood, that's what this image is supposed to relate. There's only a certain amount of mercury that are different heavy metal contaminants that can be in your food, in your seafood specifically, which is why they say don't eat salmon and tuna and whatever halibut every single day, because they are like, what do you guys call it when one level of the food changes the other part, and when the contaminants build up? Bioaccumulation, good. So this is not the top feeder, but it's one of the top feeders, so they actually accumulate more of those kind of heavy metals that the lower level fish eat. Okay, so percents and concentrations are used every day, literally every day in your life. So if you have allergies, you take Benadryl or hydro something fluoride. Huh? No. That's only for certain reasons. Anyway, there's certain percentages of that drug in the overall pill. Or if you wash your face and put a syringe in your face, that's like 2% benzoic acid. Because if it was too harsh in your skin would fall off. It's an acid. But if it was too weak, it wouldn't do anything to your skin. It just dries it out so you don't have like oil. So you guys utilize this every day. Okay, so this, we're good there. We're going to get to our pre-lab in a second, okay? Because we totally didn't get to it Friday. I'm okay with that. We have to Wednesday. So I'm going to do a quick review of solubility, factors that affect solubility. I think about like 5 slides, so let's take a couple minutes first. I did not print these for you. This is on you, okay? Now, all of this information regarding IMFs and solvents, this is the most important stuff for your pre-lab, which are on Wednesday this week. Keep your homework out because I haven't come around yet. I'm a little slow side this morning. You guys can't see. Okay, so 3 factors affecting solubility. Structure is your first factor, and structure means like molecular structure. So the structure of a molecule will affect its solubility. Well, you already know that, because if you have a solvent and a solute that don't mingle, their structures are 100% different, it won't dissolve. But if you have a structure between the solute and the solvent that are similar, they will dissolve, or they will mingle, they will interact. So if you have a polar solvent and you're trying to dissolve a gaseous solute, what would be a good example of that? Water with a gaseous solute. Okay, so dissolved oxygen. What else? Soda. Thank you. I'll put dissolved DO. Okay. So in that case, really good to have gases kind of dispersed throughout. And if you have gas particles that are very polar, I'm trying to think about what actually. I have specific stuff to tell you. If you have gas particles that are polar, then they will definitely be more soluble, because what IMF will come into play. Potentially, if the gas particle has the ability to hydrogen bond, then hydrogen bonds could come into play. What else? Dipole, right? And if you have polar molecules like water interacting with a nonpolar solute, it's going to have a lot of LDF playing into this. Water can still interact via LDF. It's not the strongest force, but it can. And of course, if you have more electrons, what does that do to your molecule? More polarizable, and that's going to increase the solubility of that particular gas particle. And so what's the most common gas in our soda? Carbon dioxide. Currently, at this point, we should all probably know the structure quite well. It's definitely wet in its polarity. Nonpolar, yeah, it still dissolves, okay? And that's because of the polarizable nature of it. And then if you have a liquid solute, it's a little bit more common, like what we consider. If things are polar, they dissolve, they interact well. Things are not polar, they don't dissolve well. And then lastly, our solid states. Generally, the rule of thumb is ionics dissolve, right? They dissociate. I do want to differentiate. I'm pointing over here on the board now. The word ionize would be appropriate to use for ionic. Maybe acids, but that's about it. Literally making ions is what that word would be portraying. Dissociate can be used for ionic, but it can be used for a lot of other things too, but it means to break into ions or break into parts as well. Solvate and hydrate mean they don't make ions. They just get water surrounded by water, and water helps bring them into solution, but they don't break themselves up into individual new particles. Okay, so in ionic compounds, most of these will dissolve, or most will ionize, but we also have some we know won't, or not very well, and that's going to be because their lattice energy is too high to be overcome by water. So this is just a quick review. What does H1 refer to? Delta H1? Breaking apart what? So the solute or the solvent? Solute. So this is taking the solute into individual particles. Like if a solute's stacked together like this, I don't care if the solute's ionic or if it's covalent. Sugar or sodium chloride is still stacked closely together, and you still have to pull them apart. Ionic, of course, you'd have to break the lattice, which would be incorporating lattice energy into the discussion. But sugar, they're still interacting via polar forces, so you still have to overcome those forces. So this is H1 is regarding the solute. H2 is concerned with the solvent, and so this is either overcoming lattice energy or IMFs of the solute. And is this going to be endo or exo? Loud and proud, people. Endo, because you have to overcome, you have to pull apart particles or break ionic structures down. And the solvent IMFs, would this be endo or exo? Right, so example, water to water, what's holding it together? Hydrogen bonding, or benzene to benzene, what's holding it together? Benzene is the diamond shape with carbons and all hydrogens around. LDF, because it's all nonpolar. So regardless, we're still pulling particles apart. This is like expanding the solute, so there's room to mingle with water or solvent. Expanding the solvent to allow for mingling with the solute. So both of these processes are endo, and we're hoping that in the end, delta H3 is bigger than H1 and H2 because we want it to be more exothermic in the process because that's more overall stabilizing upon interacting with the solvent and solute. But if you have a lower lattice energy overall, that number is going to be low. Therefore, it's going to end up making that compound, that ionic compound, more soluble. And then, of course, covalents should be polar if they're going to interact with water in any way form. So the first feature, or the first term we should consider within is something to be soluble is what? Structure, which is all dealing with basically polarity. And then, this is still regarding structure, but it's just elaborating on the organic side of things versus just like water being polar. So if you have alcohols, note the alcohols are create a polar end on an organic structure, because most time we think organic is carbon, hydrogens, carbon, hydrogens, carbon, hydrogens, which would just generally be nonpolar. So that's a really generic statement. So we have like a straight chain alkane. It's going to be nonpolar overall. Hydrophobic, meaning not going to interact with water, therefore not soluble. That's why we get like oil and water separating in addition to the density argument, but this is the bigger piece. And then the more OH groups you have, the more soluble you are. And that should probably make sense because you just have stronger IMFs with the polar solvent. And then a couple of examples of nonpolar solvents that we've been exposed to already. Benzene, what's CCl4? Carbon tetrachloride. It's just a tetrahedral structure, it's nonpolar. Toluene, we will never use in here. You'll use that in college. It's a little bit on the hazardous side, as is benzene, as is hexanes, and so forth. So we don't use a whole lot of nonpolar solvents. And can you guys imagine why?
why we as humans don't? Say again? Well, all right, so what's our body's made up of water, like predominantly within our cells. But what are our cells made up of? What's holding our cells together?
Non-polar and polar.
That phospholipid bilayer. So that phospholipid bilayer is got a little hydrophobic tails pointing in, and this is interacting with water, and this is interacting with water. But once you put a nonpolar solvent on us or within our body, respiratory system, whatever, it starts to really break up the structure, and your cells become destroyed. That's why we don't use nonpolar solvents, because nonpolar solvent will get in here, and it's basically going to attract the hydrophobic tails, and it's going to pull them out. It basically will turn the cells inside out and make them burst. Not good in general everyday life. So that's why, that's why if you get a sodium hydroxide or anything like that on your skin, then immediately your skin starts to feel slippery because it's eating at your cells. So, yeah. Okay. That's just a strong base dissolving your cells. But anyway. Okay. Part 2. So first part is structure. Second part is pressure. Think about a situation where pressure would help something stay dissolved. Like, give me a real life example where pressure helps something stay dissolved in an aqueous solution. Soda, right? 2-liter bottle, you open it up and it goes, right? You're releasing all the pressure on top. What do you start to see within the body of the bottle? Bubbles come out, right? So when it's capped, it's keeping all that pressure and all those gases that are dissolved within, and when you uncap it, you've released the pressure, you've changed the solubility of the gas. So that's what our kind of bottom part down here is going to talk about. But if you have a gas solution, like a balloon, and you have argon and carbon dioxide and oxygen and hydrogen, etc., you have all that in your system, you can change the pressure, you can squeeze the balloon, you can put it on top of a mountain, you can put it under the ocean, but these gases are not going to change their solubility. Not one of them's not like going to precipitate out and go, oh yeah, hydrogen, we're going to kick you out of the air, you're going to drop down to a solid form. That's not going to happen. So that's related to Boyle's law, because once you change the volume of the substance, the pressure is going to change in an inverse fashion. But the solubility of all of these gases will remain the same. It's just basically expanding the space that they live in. So gas solutions, like the air, are not going to change upon differences in pressure. So like at the top of a mountain, I know, we all know this, just making sure we're clear. What happened to atmospheric pressure? Decreases. What could happen if you're climbing Mount Everest and you're just hiking, okay? And they say, okay, you get kind of tired. Why do you get tired? Not because you've been hiking, please. Because there's less oxygen, right? So per space, per given volume, overall, yes, there's less gas because there's lower pressure, so it's expanded. But overall, collectively, there's still the same number of gas particles if you collect the total entity of all the gases. So they say the dissolved or the oxygen levels are lower, which is going to lead to less aerobic respiration, less ATP. Okay, so gas and liquid. This is the one that we're most familiar with. This is our soda 2-liter bottle example. And with that, we know that greater pressure helps keep bubbles in solution. Lesser pressure allows the gas pressure to inverse, so we're going to release bubbles. So basically, greater pressure, greater solubility. And there is a law for that. Henry's law. Does anybody remember this from Honors Chem? Maybe the name? No? Okay. So here is the law. So I'm going to let you take a minute there because I'm going to scroll down to see the actual law here in a second. But this is giving us a mathematical formula to back up the idea that lower pressure will cause lower gas solubility and higher pressure will cause higher gas solubility. And that is just a general rule of thumb. So if the gases are just chilling in solution and we change the pressure, the gas solubility will change as well, like in a very proportional manner. But if you start to see, so we think this is our general rule of thumb, but if you start to see the gases actually react with the solvent, we're totally changing up the rules here. We're changing up how much can be dissolved because now we have an external player, reactions, that are causing the gas solubility to change, so it's no longer proportional. So that's why we say it has limitations. So oxygen and water, they're not going to react. They're two they're two covalent species that literally just don't react. We're not making hydrogen peroxide or anything here. So this will obey Henry's law because there's no extra reactions or side reactions that are occurring. HCl and H2O will dissipate because what do these guys do together? What do they make? So this is gaseous and liquid. So we're making what? Hydronium potentially and Cl minus, right? Aqueous and aqueous. What happened to the gases? They went bye-bye, also known as they're gone, right? So the gas we started with, it's not there once the reaction has occurred. So of course we're disobeying Henry's law because there's no more gas to differentiate with the pressure changes as well. And then what does sulfur dioxide and water do? Anybody have a guess? I don't care if you're wrong, I want you to guess, come on.
Doesn't react.
It does react, give me something else. Non-metal, okay, you've got to know this. Non-metal oxides and water always make what? Non-metal hydroxides. There's no metal. Okay, non-metal oxides and so if I had CO2 in water, you would know this. What is this? Carbonic acid. See, you know that non-metal oxides in water make acids. What does this non-metal oxide in water make? Sulfur acid, because there's only 3 O's. Okay, so definitely we're taking a gas and a liquid and we're making an aqueous acid. Therefore, we're modifying the particles of gas there. So effectively, you're modifying the solubility. Non-metal oxides in water make what? Acids. Metal oxides in water make bases, metal hydroxides. I know, Unit 2, I know, but we have actually used this at some point in time in our lives since Unit 2. Okay, so this is supposed to, let me show you proportionality first. This is if you have proportional data. If you have pressure and concentration, you have to solve for the other concentration, like dissolved gas, you could do that given no other data. It's just a proportional, it's just a proportion. Increased pressure, increased concentration. Decreased pressure, decreased concentration. That's it. So if you're not given like 2 evidences of data or 2 separate conditions, you have to use this. C is equal to Kp. What's C stand for? Okay, concentration, right? So C is kind of supposed to represent our concentration, which is how soluble is that gas. It's usually in molarity. It could be in grams. It could be in milliliters. Could, because we're talking about volumes of the gas per liter. Thank you. And then K is just a constant, little k. We see little k quite often. And note the units for that. And then P is the partial pressure. And from that, we would usually utilize atmospheres. Give me a thumbs up when you go there. C is equal to Kp. I'm going to give you an example, and this is a good example, like practice problems right down. This was from the MSIRE. If you have it printed, you can pull that out. All right, so I'm going to read this to you, and I want you to tell me what's important to write down, okay? A certain soft drink is bottled so that the bottle at 25 degrees Celsius contains CO2 gas at a pressure of 5 atmospheres over the liquid. Anything? Anything here? Okay, 25 degrees Celsius, and so it's CO2 and what? 5 atmospheres, okay? Assuming the partial pressure of CO2 in the atmosphere, so that's like the air, is 4.0 times 10 to the negative 4 atmospheres, calculate the equilibrium concentrations of the CO2 in the soda bottle before and after the bottle is opened. Henry's law constant of CO2 is 0.031 moles per liter atmospheres at 25 degrees Celsius. Okay, so what was this information about? CO2 at what time? Capped bottle, right? So this is the capped bottle, which makes sense because we have a high pressure system, so it's capped. That means it's under a lot of CO2 pressure to maintain the bubbles. And then atmospherically, what are the conditions, or what are the data points? 4 times 10 to the negative 4th atmospheres. Still 25 degrees Celsius. And then what else are we given? Constant K. 0.031 molar per times atmosphere. Molar, so molarity times atmosphere is at 25 degrees. Go. So you can figure out the concentrations. Find the concentrations of both of them. Alright, Andrew's table, get me started on what you guys are working on.
Don't you just set it up to where C is safety?
Okay, so C is concentration, K is the constant, P is the partial pressure of whatever we're dealing with. Okay, so what am I looking for?
You're looking to find your atmospheres, and I mean, you already have your constant, so you plug that in for J.
Okay, and what else do I already have? I already have the P of pressure for the capped bottle. So what am I mathematically doing? Just plugging in. So 0.031 molar times atmosphere. Molar. That's sorry, that is per atmosphere because there's a slash. And then pressure is 5 for the closed bottle. And that should make sense because atmospheres must cancel because concentration is established in concentration. What's that concentration? What is it? 0.155 molar of CO2 in the closed system. JT's table, pick up from there.
Then I think it says after, right, the pressure changes to 4 times the main force.
Substitute the other one in atmosphere. And what is that pressure, or what is that concentration?
1.24 times 10 to the negative 5th.
Times 10 to the negative 5th. Atmosphere, or constant molarity. Okay, and so what we're basically indicating here, guys, is that as you relieve the pressure, what happens to the gas solubility? It's going down. And we know that qualitatively, and now we know how to do it quantitatively. Now, if we had been given one of the concentrations already, like we had solved here, because we did, and we didn't want to use K again, we also could have done the P over C is equal to P over C. Because we have two partial pressures, we have essentially two concentrations. Good here? All right, I have like one more factor to consider. So first two factors that affect solubility are what? Temperature and pressure. Okay, temperature is the last piece, which we probably knew that because we talked about the solubility curves. The solubility curves that indicate saturated, supersaturated, and unsaturated, and temperature is a variable on that graph. So if you have gases and gases mixed together and you increase the temperature, what happens to those gases? They move faster. Increased temperature, move faster. So eventually, we're going to get to the right word. What's the word I want to use for this? Increase average kinetic energy. And that's going to happen just for some gases or all gases? All gases. So if they're all mixed in together in a slow fashion or a fast fashion, low or high kinetic energy, they're all going to be the same solubility. We're not changing who's dissolved within each other. So that's why this temperature change has no effect on a gas-gas solution. But if you have a gas-liquid solution, what does the solubility curve look like for a gas-liquid solution? Slopes downward. Most of our, our solids slope upward. This was the temperature. No, this was the temperature, and this was solubility. This was what we talked about Friday. And so solids all increased up, but gases, you guys said, went down. And that's because as you increase temperature, why does solubility go down? What's the background? What's the reason? Good. So if you increase temperature, it increases the kinetic energy, or the average kinetic energy of the gas particle. And then those gas particles do what? So they're breaking through the what on the surface? Surface tension, because they have the most energy. They break through surface tension, pop, they're out. They're no longer dissolved in solution. Gas solubility has decreased because they're evaporated. So they just need a lot of energy to do that. Solids, when they get moving faster, they don't evaporate. They just move faster in solution. They're chilling there. So remember, that's an inverse process. Now, we do have a solid liquid solution that's going to be dependent upon if it's an endothermic process or an exothermic process if it will change solubility high or low. So let's write down a sample or an example here for an endothermic reaction. What's a good endothermic solution process? The one you have to remember. Ammonium nitrate. So ammonium nitrate, solid, under aqueous solution will break into what? NH4 plus and nitrate. Okay? Alright, so this is our case. This is an endothermic process. Where, if I were to put temperature or energy someplace, where would I put it? Reactant or product, guys? Reactants, because if we're using it as a reactant to force this reaction in the forward direction. So I'll just put like 100 kilojoules here. Okay, so here's our process. If I increase the temperature on this system, what will happen to the solubility of ammonium nitrate? So it's going to shift right. Okay, so if you increase the temperature on an endo process, do you guys remember the phrasing we have to use for this? It favors the what? So increasing temperature favors the endo direction, which for us is the forward direction. So what are we doing to solubility? Increasing solubility, because we're basically shifting right, and that's going to cause more ions to be favored. So you probably can figure this out. What's going to happen with an exothermic process? Favor the what? Magnesium sulfate. Solid makes magnesium ion and sulfate ion, and that's a negative, and heat. So if I increase heat, which way does it shift? Shifts left. So what does it do to solubility? Decreases solubility, because again, the same phrasing matters, the same phrasing applies. Increasing temperature favors the what direction? Endothermic direction, which is which direction here? The reverse, because if you follow the reverse reaction, you're consuming heat, which is indicating it's an endothermic process in the reverse fashion. So we favor the reverse, then we are favoring the solid magnesium sulfate. Good review? All but Henry's Law? Seems like most of this is review. Okay, and then now go to your computers. I think this is where we are. So I'm going to do part 1 of the lab. Ask you guys to do part 1 of the lab, and we'll figure out how much of part 2 we'll get to today, because I have some time built in tomorrow too. But essentially, what we're doing is one of our last inquiry lab. Oh my gosh. Woo. Keep it together, guys. Okay, so the last inquiry lab is we are taking, we're taking things, we're making a mixture, and your job is to separate the mixture. And if it doesn't separate well, you gotta tell me why. If it does separate well, you gotta tell me why. Everything is gonna be based on IMS, or solubility. Because solubility is heavily dependent upon IMS, right? So IMS are gonna rule our explanations and rule our reasonings and conclusion, etc. So hopefully you are going to that Billy address. I'm not sure I linked it under today's homework, so that Billy address would be where I would head now. Yes, thank you, because we were supposed to get to it Friday, we didn't get to it. So essentially you've been selected as a secondary CSI team, because the first ones were crap, and your job is to try to get some results of a situation where they had something found at a crime scene. That's your premise. And in your laboratory CSI investigation, you have to use some solvents. And those solvents, there are many choices. I'm going to hand you the lab sheet itself, which has more information. The solvents, you have many choices, but you are only going to use 2 because you're going to try to be, cost efficient. And you are only allowed to use 20 milliliters of those solvents that you've selected. So those are your limitations for the procedural aspect of this. But before you even get into the procedural aspect, you'll notice there are 2. The first doing the teacher demonstration, because this is chromatography. You've seen chromatography before, either an honors chem or a Leave It here. Your job is to, first off, watch 2 quick videos. They're like 5 minutes total. And then you're going to look into this simulation to indicate what's happening in the chromatography-based experiment. So we're going to start here, okay? And right now, you can work with a buddy just to talk about some things and so you guys can compare notes, but work on your own independent Google Doc for now so you guys can do scripts. I would think you'd want to do this on a Google Doc so at the end, when you do get in groups, you can compare notes very easily. So let's see where we are in 10, okay? All right, come back to me and start writing down what's on the board. This is our next topic. So let me just recap for the lab aspect. Hold on to your paper because tomorrow we'll actually need to look at these diagrams, like on the molecular diagrams on the lab sheet itself. And tomorrow we'll actually group up. We can team up and make our procedures a little bit. It is contingent on like us trying to get started pretty fast tomorrow. However, our lab is actually on Wednesday. So I have under homework day 2 problem set, which I'm questioning if you need more with that, but I have another one that's actually going to replace that. And then pre-lab, we didn't quite finish through that simulation of pre-lab. That's accessible at home. The molecular consortium is a Flash or Java-based piece of software, and I do not know that you can access it at home, which is why I have to make sure you have some time in class tomorrow. Okay. All right. So who remembers colligative properties from honors chem? Okay. What are some of the ones that you remember? Boiling point, elevation, freezing point, depression, and that's probably the 2 that you remember. In AP Chem, we talk about vapor pressure lowering a lot more. Like, I was like, hey, there's this one called vapor pressure lowering. You're like, great, and I didn't tell you any more in honors chem. That was it. But we actually never even learned about the 4th one, which is osmotic pressure. But you've heard of osmosis before, right? It's the flow of water from high concentration of water to low, okay? Makes hypotonic solutions, hypertonic solutions, and isotonic solutions. So now we're talking about the pressure that actually allows for water to flow within cells. Okay, but that's going to be like, those are topics for more for tomorrow. We're going to talk about vapor pressure lowering today. But to get into this, we have to understand what a colligative property is. Normally a pure solvent is a pure solvent. It's got a physical property. For example, what is the boiling point of water? 100, right? 100 degrees Celsius. But we know that when we make a solution, like water with salt, sodium chloride, it can vary the boiling point. So this is basically these are collective properties or properties of solutions based on the pure solvent. Like, we know the pure solvent, but when we make it a solution, it modifies the property a little bit. And so we have to understand that the solutes that we're putting in are the most important piece to know more information about. How many particles are going in? What kind of particles are they? What are they doing with water or with the solvent? So we need to know what they are so we can determine if they're covalent or ionic. So the pure identity doesn't matter, but the characteristics they contain do matter. Because if something's ionic, what does it do, let's say, with water? Forms ions, right? So like sodium chloride and magnesium chloride, they would ionize, okay? But they ionize differently than between the 2 of them. So what does sodium chloride ionize to form? Sodium plus and Cl minus. How many ions have formed? 2. We call that an I of 2. I means the Van 't Hoff factor. Van 't Hoff factor. Guess who discovered it? Mr. Van 't Hoff, right. So if you have an I of 2, that's great. But what about magnesium chloride? What does it make? Mg2 plus and how many? 2 chloride ions. So it's 1, 2, 3. There are 3 ions formed, therefore I is 3. So this is going to make a more significant impact on the solvent's properties than an I of 2, because the greater number of particles, so usually with this, the greater number of particles makes a bigger change, which we're going to decide is the change high or low. So are we doing freezing point depression or boiling point elevation or vapor pressure lowering? Whatever the system is, we have to kind of based on the characteristic we're describing. How does glucose interact with water? So does it ionize? Okay, which word might I use? Okay, so not ionize, not necessarily dissociate, because that still means breaks. It's probably going to be hydrated by the water itself. So the crystalline structure of glucose is staying intact, but the hydration of it is going to make it look like it disappears. So like we put a lump of sugar in water and it disappears. Well, it's not ionizing, it's not making ions because it's non-conductive. So the glucose itself gets hydrated which means surrounded by water. But it does not break the C6H12O6 structure. It just pulls glucose molecules away from glucose molecules away from glucose molecules, which some of you guys even indicated on your What's in the Bottle lab, which was fantastic before this. Okay, chelator properties are properties of what? Solutions, thank you. So we have to know kind of what's going into solution to make this change occur. So before we jump into vapor pressure, what is vapor pressure? Long crowd here. Talk in your groups first, because I got like 2 people helping me over here. Talk in your groups. And think about how can you change vapor pressure. Talk in your groups how you could change vapor pressure. All right, and come back to me. 3, 2, 1. Front table up here. What's vapor pressure?
Pressure where something vaporizes.
What's pressure? Collisions with the container wall. So is this container open or closed? Let's call it closed, because if not, we have an uncontrolled system because the vapors are escaping and we can't really account for any pressure changes. Closed system, vapors are being formed through just natural vaporization, or maybe we've heated it, or let me say temperature, and we're forming vapors. They're colliding with the container wall, boom, we have pressure, right? What types of substances would naturally have a higher vapor pressure? Weak IMS, like what? Oh, very specific too. Okay, CCl4, so nonpolar solvents, or nonpolar things with weak IMFs. Strong IMFs would naturally have lower vapor pressure because they stay collectively attracted better. All right, so I've got a picture for you. Okay, so glass container, sealed, vaporizing. And then this is a pure solvent. Can you tell what it is? Look, it's the Mickey Mouse one, right? So that's water. And if you heat it up, there's going to be more of them vaporizing, right? So essentially they're vaporizing, condensing, vaporizing, condensing. This is physical equilibrium. Okay, so this is just a closed system, and there's an equal rate of evaporation. That rate is equal to the rate of condensation. And so in the end, we establish one vapor pressure, and that's it, at a particular temperature. But once we change temperature, what do we do to vapor pressure? Change it. So everything vapor pressure related is established at a particular temperature. The temperature may not be important at all to us, but we understand that it's an important fact to note. And then I just wanted to ask you what this term right here meant. So non-volatile means what? They don't evaporate, okay? So if I have a solvent that naturally evaporates like water, and I put a non-volatile solute in there, it's gonna what? It's gonna hang around and not vaporize. But water is pretty friendly. It interacts with a lot of things, right? It interacts with ionics, it'll interact with covalents, even though just not strongly, but it still will. So what do you think a non-volatile solute will do to water? It'll interact with it. It's like, hey, hang out with me, interact with me via London dispersion or whatever. And so what does it do? It makes water what? Not evaporates fast, therefore does what to the vapor pressure? Decreases it. The moment you put a solute in, any solute will have a minimal attraction or a maximum. I mean, there's a range of attractions, but the solute and the solvent will interact. And in those interactions, we have adjusted the vaporization of the solvent, which would then overall, the rule of thumb is overall, these solutes and solvents interacting will lower the vapor pressure of the solution. The solvent has one vapor pressure, boom, it's evaporating. We see it vaporizing, we see its vapor pressure. The minute the solute interacts with the solvent, it mingles, it interacts via strong or weak IMFs, it lowers the vapor pressure. That is vapor pressure lowering. Got it? Okay, so with this comes some equations, Raoult's law, and I think I printed like on the 3rd page of the packet something for you. And I think it's this. What should be lying to you? But regardless, if you don't have it, then this is important information to write down. So the rule of thumb is as you increase the non-volatile solutes, you're decreasing the vapor pressure of the overall pure solution, so it's no longer pure. So non-volatile would be things like what? What things don't evaporate well? Sodium, what? Chloride, anything ionic. Okay, ionic things don't evaporate well. Covalent things do evaporate well, but we're still in the end trying to indicate we're putting liquids and solids into the solution, because a gas is obviously already volatile. It's going to naturally increase the vapor pressure. All right, so here's your rule, or here's your law. This is not quite Raoult's law yet, but it's a version of it. So essentially, we're looking at the pressure, the vapor pressure. P stands for vapor pressure. P of the solution, and how does that relate to the original pure solvent? Well, your pure solvent has a little knot to indicate pure, original, and you multiply the pure solvent's original vapor pressure by the solvent's mole fraction for the solution. So if I've got 4 parts overall, 1 part solute, 3 parts solvent, let's call that mole fraction. You'd have 3 parts of solvent over 4 parts total, and so your mole fraction would be 75% or 0.75. So you'd have to find the mole fraction of the solvent to say how much solvent do I have remaining, like proportionally, multiply it by the pure solvent's pressure, and you get the new solution's partial pressure. This one will always be what? Higher or lower? Lower, because you're multiplying the pure by a fraction or by a decimal. So it's always going to be true. So there's your definition of terms. You need that right there for yourself. Yes? Thank you. Okay. So other than that, I know you guys know this now. We love linear regression. We love linear line in chemistry because it gives us great predictability. So we can predict basically anything from a linear regression line. So this equation is actually a linear line. It's just we indicate the 0 by that 0 being the y intercept. We indicate that by not putting anything over here. So from a graph standpoint, P of solution is equal to P solvent times mole fraction plus 0, which is the y-intercept. So what is the slope? Pure solvent, right? So this is M. Pure solvent is M. So we'll look at some graphical examples of this in a moment. So this is our general rule, but again, we talk about interactions between solvent and solute. There's a range, strong interactions and weak interactions. So do you think strong interactions or weak interactions will cause the greatest depression of vapor pressure? Strong interactions between solute and solvent or weak interactions between solvent and solute will cause the greatest depression of vapor pressure? Strongest would, right? So we know that's true, and we have to understand that we can predict that, but we may not always be able to calculate it. But we definitely know that interactions between the solvent and solute can skew our predicted pressure, vapor pressure. Okay, so we're going to talk about this more in a second. Can I scroll down? Okay. Eventually, we'll see how we can actually use this data to find molar masses of certain vapors and things like that. So we'll get there shortly. This is the one I want to do with you guys, okay? So the vapor pressure at 30 degrees Celsius, why am I telling you the temperature? Huh? It's temperature dependent, right? We do not use the temperature, but it's always going to be given to you, provided to you, because that's how vapor pressure is going to be adjusted. The vapor pressure of water is 31.8 millimeters mercury. What is the vapor pressure of solution prepared by 396 grams of sucrose and 624 grams of water? Go. I'll try to get 2 bombs over here before we leave today. You have your equation at the top of your paper if you've forgotten what you're solving for. I'll help you out with molar masses if that's, is that helpful? Yeah. I know. Okay. What equation are you guys using? P. A, but we don't know what A stands for yet, so P solution equals X, who's the solvent here? Water. This is helpful for you to identify it as you go. Times P naught of solvent, which in this case is who? Who's the solvent? Water. Sucrose is in lesser amount. Remember, the lesser quantity gives you the solute, the greater quantity gives you the solvent. So we already know this, right? This is what? 31.8 millimeters of mercury. And you know these quantities here. Okay, so to get mole fraction, what do we need? Moles of who? If I'm finding a mole fraction of water, who do I care about to be the part I care about? Water, right? So this is moles of water. And so that's going to be our numerator divided by moles of water plus moles of sucrose, which you're saying is total moles, right? So 624 grams of water, 18.02 grams per mole. What is this? 34.6 moles. Don't cut me, don't cut it too soon because you'll have rounding error. So 34.6 moles of water. And then what's our molar mass of sucrose, anybody? So 396 grams of sucrose, 342 point what? 176 grams of sucrose per mole. That gives us 1.16 moles of sucrose. Now you have the two pieces you need to build this fraction. So 34.6 moles of water over 35.76 moles. What's that fraction? Actually, it doesn't really matter. You can just plug it in. Plug in this fraction times the vapor pressure, or the original solvent pressure. Vapor pressure. What's that? 31. Should it be higher or lower? Lower, and when you guys get 30.8 millimeters of mercury for the solvent, or for the solution. And so again, why is this lower? Because what? Well, because we're multiplying by a fraction, but chemically, what's happening? So sucrose interacts with water, so there's less water particles that are vaporizing, because they're basically, you're lowering their kinetic energy, so they can't vaporize as easily because they're interacting. Yeah.
If sucrose was not polar and the ions were in dispersion, wouldn't that wouldn't the hydrogen bonds be more likely to keep it from vaporizing?
So water would attract with water more, and sucrose or whatever compound, lung dispersion, would interact with lung dispersion more. We're going to talk about deviations from Raoult's law tomorrow. Okay. All right. So last thing, I think, definition of boiling, because it does relate to vapor pressure. Okay. So in terms of boiling point, somebody next to you go like this, and somebody on the other side go like this. I think we've done this before. Have we done this before? Here, Darcy. Alright, so Darcy's going to be my vapor. She's trying to vaporize, but I am the atmospheric pressure, and I'm holding her down. Okay, so I'm holding her down. The vapor pressure is trying to push up, I'm like holding her down. So when does she boil? When does she escape? When she can overcome the force of pressure that the atmosphere is causing. So when they are equal, she can start to boil. Okay, so the temperature that causes the vapor pressure to get up to the point where the atmospheric pressure and that are equal, then you have the temperature at which the substance boils. And we'll pick up from here tomorrow. Okay. So what I'm expecting for you guys tonight is we're not going to do day 2 concentrations because I think you guys got the concentrations. Look for the one called pressures. I took a picture of it up here. Hold on. You cannot do very much of this, I promise. You can do some though. Okay, so on this one, do you see it next to the day 2? It's next to day 1, next to day 2. I still have like 4 minutes with you, so hold up, don't pack up yet. So you can definitely do that one because you're given all the information, and this is again practice with concentrations. You can do, I didn't copy them all. You can do as much as you possibly can, okay? Do as much as you can, because there's only a couple of vapor pressures on there that you can do, and just literally those examples. Yeah. Okay? And so during the intervention today, we're going over the active basic Bolivia test, and clicking the contract with you. Do not leave that at home. So we can totally turn that in, you know, in a couple of days. So you don't have to do that over break. Margaret had it before time. Okay. So the last bit of time is yours. You can stretch and do some yoga. It's up to you. Thank you for your attention. I am trying to get as much done before break as I can.